problem 49, page 328. Here we have a uniform solid disk. It's a disk of radius r and a mass m, is free to rotate on a around a pivot point here at the edge of the disk. It's not at the center, it's at the edge here. We have the axis. So the system will move down like this. This is the horizontal position as initial position, and this is the vertical position as final position. Okay, we have a motion down. What is the speed of its center of mass? VCM, how much? When the disk reaches the position indicated by the dashed circle. So I need to calculate the velocity of the center of mass at this position. Initially, here, this is the initial position. At this position, we have V equals to O and omega equals to O. We released the system without initial velocity. Okay? When the system moves down, here we get the final position. As the final position, as you see, here we have the center of mass, and here we have the center of mass. I need to calculate the velocity of the final position of the center of mass, where we have a rotation, as you see, clockwise. Okay, clockwise, omega. Okay, let's start with this part A. We have to find VCM. Look here. The center of mass during the rotation will have a rotation like this. From this point to this point. Okay? Like this. The radius of this rotation, as you see, is like this. Will turn with a radius equals to capital R. So we can say directly, and the velocity at any point is tangent to the trajectory. So initially start tangent. Okay, we don't have velocity initially, but after tangent, 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 tangent. So it's tangent. I need to calculate VCM at this point. So here we have a circular motion with a radius equals to R, like this. You can say directly VCM equals to R times omega. Here I want to calculate VCM. I don't have the value of omega. I told you before, if you want to calculate V or omega, you can apply the conservation of mechanical energy. Delta mechanical energy equals to 0. If we have friction, we have to put omega F. If we don't have friction, you can say equals to 0. I told you here we have a frictionless pivot. So mu equals to 0 between the x and the object. We don't have friction. In this case, we have a conservation of mechanical energy of the whole system. Okay, so mechanical energy initial equals to mechanical energy final. So the kinetic energy initial plus potential energy initial equals to kinetic final, potential final. Always the potential energy of the system must be calculated in terms of the center of mass. Okay? Look here. Here, the initial position. Here is the final position. So we put the lowest point as a reference. So the height between the initial and final, initially we have a height equals to R. Okay? So initially we have a potential equals to mgr, the center of mass, and here center of mass. What about the kinetic? We don't have velocity initially, so we don't have kinetic. Equals. Here, I told you if we have a pure rotation, so we have only a rotational kinetic energy, have I omega square. In the case of pure translation, we have translational kinetic energy, have mv square. If we have translation and rotation, in this case, we have to add have mv square plus have I omega square. In this case, we have only rotation because we have a fixed point. We have a fixed axis. When we have a fixed axis, so we have only rotation. In the case of pure rotation, we have fixed axis. In the case of pure translation, we have sliding. We don't have a fixed axis. In the case of rotation and translation, we have rotation and translation. Okay. So in this case, we have only have I omega square, and at the final position here, we don't have a height of the center of mass, so equals to 0. I can calculate easily the value of omega. So omega square equals to mgr times 2 divided by I. Listen, here I equals to ICM plus MD square. ICM is given, and D is the distance between the center of mass and the axis, which is equal to R. So here we can say R. I can give you ICM, or I can give you the total value of ICM plus MD square, okay, which is equal to 3 over 2 MR square. This is a summation of ICM and MD square. Okay, so we can say finally omega equals to mgr R divided by 3 over 2. Okay, m equal, okay, I took the same m. Okay, here we have small m times r square. Okay, equals to m and m equals 4 over 3 g divided by r. This is the value of omega. Here I ask you to find what is the speed of its center of mass when the disk, okay, I need to calculate this omega, okay, it's not the speed, it's not v. Here I need to calculate v, vcm. You know, at this position we have omega equals to radical 4 over 3 g divided by r, and at this position we don't have omega, so vcm equals to r times omega. I told you because we have a rotation about this center equals to r, the radius. So equals to r radical 4g divided by 3r. We can put this inside. We get 4g divided by 3 r squared divided by r equals to r. This one is v of the center of mass. So here we calculated omega and we calculated v. Okay. Okay. Here, what is the speed of the lowest point on the disk in the dashed position? In this position, I want to find the speed of the lowest point. Let's say this point is a point A. Initially, this point is here, A. When we have a rotation, so look well. Here we have this point. We'll turn like this. We arrive here. What is the radius of this rotation? As you see, here we have a rotation of this point in terms of the axis with a radius equals to 2r. From here to here equals to 2r. Okay? We solved one example when we have a road. We have an example with a road, and we can apply the same calculation. You can see the example in your book. Anyway, so VA as the lowest point here equals to RA times omega. RA equals to 2R times omega, which is equal to let me see, equals to M and M. We have 4G over 3 divided by R. Okay, so we can put 2R inside. We get 4G divided by 3R. times 4r square. Okay, we get here 4 and 4, we have 16. We have 16 divided by 3 gr m per second.